the last thing I want to talk about with regards to a microscopic understanding of entropy is how entropy is related to the concept of equilibrium. To do this, let's discuss, two different sorts of systems, or two different sort of macrostates of an ideal gas. Where the macrostate on the left here, let's imagine that all our molecules are at the same spot in the system, right? So with an ideal gas, particles can overlap one another, right? And so let's imagine the case where they're all exactly at the same spot, right? So they're all in this coordinate. We'll then compare that to the case where our molecules are spread out over the entire volume of the system, okay? Right? So on the left here, the molecules only take up a small volume. On the right, the molecules take up a big volume. Okay? And as you remember from when we first talked about the multiplicity of molecules, is that the number of different ways that we can arrange a molecule is proportional to its volume raised to the number of molecules in that system. Okay? And so, if the volume on the right is bigger than the volume on the left for these macrostates, that means that the number of ways we could arrange the molecules in a big, if they take up the entire volume of the system, the number of ways we could arrange them is going to be larger than the number of ways we could arrange the molecules if they only took up a small volume in our system. Okay? All right, and so with that in mind, that's the omegas. But it's a bit easier to think of this description in terms of entropy. And so if we compare the entropy of the big system, compare that to the entropy of the small system, what we would get is that S big minus S small would be equal to NKB, natural log of V big divided by V small. Okay? And since V big is greater than V small, the natural log of that is going to be positive. And so this change in entropy is also going to be positive as well. Okay? All right. So the system in which the molecules take up a bigger volume, that's going to have a larger entropy than the macrostate where the molecules only take up a small volume. Okay? And so the reason I bring that up is because we have to remember that at the thermodynamic limit, which is when the number of molecules in our system approaches that limit of infinity, only the most probable macrostate is observed. Okay? So our omega n is maximized. Right? And so for the case where omega n is maximized, the entropy of that system would be kb ln of omega max. Or otherwise, that would be the case where entropy is also the maximum number. Okay? And so what this means, there's kind of two different ways to explain this. Right? And so at the thermodynamic limit, I'm just going to tell you that the thermodynamic limit is analogous to saying that your system is at equilibrium. And so at equilibrium, or one definition of equilibrium, would be that only you're at equilibrium if you observe the macrostate that S max is observed. Or maybe a more direct way of saying this is at equilibrium, entropy is maximized. right? And so that is an important concept, and that actually guides, a lot of the phenomena that we see in the universe. And the reason that, heat travels from high temperatures to low temperatures, or um, you know, molecules will diffuse from high concentrations to low concentrations, is because they're moving in a way that maximizes the entropy of the universe. Okay? All right, and so I just sort of told you this, but we'll actually prove this to ourselves when we get to chapter 7.